When we want to analyze a real-life or imaginary experiment whose outcome is governed by chance, probability theory is useful. We may construct a model for the experiment using probability spaces. By drawing conclusions about the mathematical model, we gain information regarding the actual experiment. Often, we are not interested in the precise outcome of the experiment, but rather an aggregation of the information contained in the outcome. This is where random variables come in. Roll a die twice. Suppose that you're playing a game where the sum of the two rolls matters. A probabilistic model for the experiment may look as follows. The set of outcomes are simply the pairs of integers from 1 to 6, and each outcome has equal probability. We're interested in the sum, which is given by a function x of the outcome. In general, a random variable is a function which to each outcome assigns a real number. The random variable does not come with a specified distribution. Its distribution it inherits from the probability measure p associated with the experiment. Indeed, in the experiment above, the random variable remains the same, but its distribution will differ depending on whether p corresponds to the roll of a fair or weighted die. A probability space consists of a set omega representing the outcomes of some experiment, a collection f of subsets of omega that correspond to the events that we allow ourselves to measure, and finally a probability measure p which assigns a probability to each event in f. When omega is finite or countable, we may assume that all subsets of omega can be measured. In general, that is not possible. For consistency, we always require f to satisfy the conditions of a sigma algebra. That is, f should be closed with respect to the operations of taking complement and countable unions. This will guarantee that we will not end up with a set that we're not allowed to measure by means of the usual set operations. Let omega f and p be a probability space and x some function. Suppose that we want to compute the probability that x takes values in some set b, subset of the real line. Since p assigns values to subsets of omega, we need to interpret the event that x takes values in b as a subset of omega. Since p is a function from f to the interval 0, 1, we are only going to be allowed to measure the event that x takes values in b if this is a set contained in f. In the discrete setting, this is not a problem, since we may assume that f contains all subsets of omega, but in general, we need to be more careful. We are typically interested in x taking a specific value, or taking values in some interval, so we want to be able to measure x in I for every interval I. Again, we do not want to end up measuring a set that we're not allowed to measure as long as we restrict ourselves to the usual set operations. Hence, for consistency, we want a collection of sets B for which x in B can be measured to form a sigma algebra. The smallest sigma algebra on R that contains all open intervals is the Borel sigma algebra, and which we denote by B of R. Based on the above discussion, we arrive at the following definition. Let omega f and p form a probability space. A map X is a random variable if the pre-image of B belongs to the sigma algebra F for all Borel sets B. As it turns out, To verify that the map X is a random variable, we do not have to verify that the event X takes values in B belongs to the sigma algebra F for all Borel sets B. It will suffice to check the intervals from -infinity to X for all X. The rest will follow automatically. Let omega f and p form a probability space and let x be a random variable. Via x, p defines a measure μx, where the measure of a set B is simply the probability that x takes its value in B. This does indeed define a probability measure and is referred to as the law or distribution measure of x. Another well-known object is the function fx, which equals the probability that x takes a value less than or equal to little x. This is referred to as the distribution function of x. Toss a coin n times with probability p of coming up heads. A probability space describing this experiment is given by the set of binary strings of length n, the set of all subsets, and a probability measure which to an outcome containing k heads assigns probability p to the k 1 minus p to the n minus k. Let x denote the number of heads in the n tosses. Since omega is discrete and f the power set, x is automatically a random variable. Consider the probability space where the interval 0, 1 is equipped with its Borel sigma algebra and p denotes Lebesgue measure. Lebesgue measure is the measure where the measure of an interval is simply its length. Let x denote the identity function. This is a random variable, since for every Borel set, the event that x takes its value in this set is simply the restriction of the set to the interval 0, 1. Let y be the function which takes the value 0 on the first half of the interval 0, 1 and 1 on the latter. Again, y is a random variable, since the probability that y takes its value in a Borel set is an interval. The distribution functions of x and y can be computed as follows. We find that the distribution function of x is the linear functional on the interval 0, 1, while y takes the values 0 and 1 with equal probability a half. We recognize the distributions of x and y as the uniform distribution on the interval 0, 1 and the Bernoulli distribution with parameter a half. Above, we gave a precise construction of random variables on specific probability spaces. However, that is not how we are used to work with random variables. Often we introduce random variables without reference to a specific probability space. We then assume indirectly that there exists a probability space where the mentioned random variables are defined. We don't care so much what this space is, just that the random variables have the prescribed distributions. One concern, however, is that in order to assume that such objects exist, one has to verify that they do. Above we saw concrete constructions of random variables with binomial, uniform, and Bernoulli distributions. However, there are more systematic ways in which random variables with a prescribed distribution may be constructed. Let us first recall three properties that the distribution function of a random variable necessarily satisfies. First, it is non-decreasing. Second, it is right continuous. And third, the values of the function, as we send x to -infinity or +infinity, are the values 0 and 1. Consider again the probability space where the interval 0, 1 is equipped with the Borel sigma algebra and p denotes Lebesgue measure. Let f be any function that satisfies the properties 1 to 3. We define the generalized inverse of f as the function which to a value u returns the infimum over all values x such that f of x exceeds u. We make two observations regarding the inverse. Since f is non-decreasing, so is its inverse. And since non-decreasing, any set of the form where the inverse takes a value less than or equal to x is an interval. So the inverse is indeed a random variable on this probability space. In fact, using also that f is right continuous, one may show that the random variable being less than or equal to x corresponds to the interval 0 f of x. Hence, the distribution function of the random variable indeed equals f, which follows since the probability p assigns to an interval is its length. In conclusion, we have taken a specific probability space and defined a random variable x, whose distribution function is given by f. A less specific, but equivalent, statement is the following. If u is a random variable, uniformly distributed on the interval 0, 1, then f inverse of u is an f-distributed random variable. Equipped with the knowledge of how to construct a random variable with a prescribed distribution if needed, we can safely continue to introduce random variables without reference to a concrete probability space.